Okay, there we go. Fixed it. Sorry about that. So we are back on the air, and thanks for letting me know. Good, we're all set. We're back on the air. That's great. Now, I'm going to be running this and looking for questions as we go. And if I miss any of you, let me know by raising your hand, and appreciate the feedback. Okay, so here we go. This is the agenda, and we're going to walk through each of these items. And without getting into much of the detail here, we're going to include a few definitions. We're going to explain the devices, or give you a list of devices that are more prone to class 0 sensitivities than others. We're going to give you a brief review of the charge device model and charge board event, and then we're going to get into who's at risk. And you'll see that we're looking at this from a few different perspectives, and then briefly, what can we do about it? Okay, to begin with, there are a few acronyms that will come up during this presentation. One is EPM, the ESD Program Management is what it stands for. It also is the title of my book, which many of you have, and thank you. It reflects my conviction that quality systems are critically important, especially for class 0. It is essential that you have a robust compliance verification strategy and that you're measuring the right things. We'll also talk at points about our best practices benchmarking. This is a strategy that we developed originally for AT&T and has proven to be 90% accurate, even over the phone. It's a very interesting strategy. And then here are a few acronyms that I expect most of you are familiar with. And I would start by saying that we view electrical overstress as an overarching issue where the various ESD stresses and models that we're aware of are subsets. So all of these ESD acronyms are subsets of the electrical overstress situation. Now, the slides are changing, Henry. Let me know if there's a problem there. It sometimes takes a few seconds for the transition, so I'll pause in between. Okay, we're now on slide 4, and oops, somebody's got his hand up. Let me see who that might be. Okay, Dave. I'll put on both at the same time. Dave Best and Dave Best, let's hear from you first. Dave? Let me just check the question box again. Not seeing any slides. That's strange. Hang on a second. I'm going to shut this off. Okay. Still on slide 1. Well, I'm going to do this. I'm going to shut off the screen and then turn it back on. Sometimes that resets it. Let me know if you can see a slide. What number is it at this point? Slide 4. Okay. Great. Thank you. Excellent. Okay. We're back on the air. Here we go. Thanks for letting me know that, folks. And I've lowered all hands, so if anybody wants to talk again, let me know. Okay. So here is slide 2, and these are the definitions that my team put together. We have class 0, double, and triple 0. And very recently, the ESD Association and JEDEC have issued a joint standard on HBM stress testing, where they have come up with these additional definitions, class 0B and 0A, for these two categories. And what we have found is that the failure rates and the in-house and for reliability tend to escalate at these three breakpoints. Now, we're talking about withstand voltages for either HBM or CDM. So it's important to consider both, and again, our experience has been that the issues tend to escalate at these breakpoints. We've also found that class 0 devices are prone to higher levels of test failures, which I think is pretty straightforward, as well as test escapes, meaning that devices that were damaged perhaps, but were not, the areas that failed were not part of the test vectors for the test program. Because of the higher failure rate for class 0, test escapes tend to happen more often, and latent failures are also more prone to occur, which we'll talk about a bit in a moment. Okay. How about the trend? Where are device sensitivities going as we look into the future? The ESD Association has a technology roadmap that you can go to the website and get in detail. But here is a summary of it. This is an approximation of the numbers on their charts. And you can see as we go, look from 1992 onward, the HBM sensitivities are falling. CDM sensitivities are also falling to right down into the class 0 region. So the trend toward class 0 is here. It's escalating as we talk. Now, what are the IC suppliers using as target levels for their design? And here is the transition that has occurred largely through the work of the Industry Council, which has done some really good work, and there are white papers available on the ESD Association website. So looking at these numbers, you see that CDM is that their target level for design is class 0. It's at 250 volts. So going into the future, you can expect more and more of these class 0 device sensitivities, especially for CDM. And of course, HBM will also have many class 0 devices. Here is a list. This is slide 6. Here is a list of devices that are more prone to class 0 sensitivities. And of particular interest is the optoelectronics. They are much more prone to latent failure than some of the other technologies. So in general, if you have optoelectronic devices, we would recommend considering them as class 0, even if you don't have the data. Now, some of you may be aware that the most sensitive items in the world are TMR heads, and they fail in their withstand voltage is in the range of 1 to 3 volts. Now, looking at LEDs as an example, Sylvania has application notes that I've taken these photos from, but you can see here are some LEDs where this one in the center does not have the intensity of the others. It has been damaged with ESD and prematurely failed. And others on this here, this strip down here, you can see actually were catastrophic. So again, to repeat, optoelectronics in general pose a high risk of latent failures in time due to prior damage. Okay, industry standards. S2020 is the best industry standard for manufacturing practices. However, in general, standards lag the technology by as much as 10 to 15 years, and S2020 is no exception. Even the S2020 will be updated this year, and there will be a new issue coming out that will still be at least 10 years behind the times, 10 to 15. And there are good reasons for it. It takes time, and if you make changes too swiftly, it can be very disruptive. One of the issues with 2020 is that it is primarily an HBM document. The scope of it is limited to that, and protection for devices at or above 100 volts. Now, one of our attendees sent a question in prior to the webinar asking about this 100-volt number and the data that was used to support the decision. Some studies, some limited studies were done varying resistance to ground and monitoring body voltage. And by doing that, it was found that if you are at 1 megohm or less, the body voltages did not exceed 100 volts. So unfortunately, there is no paper available that I'm aware of, and the background work that was done on this 100-volt number is somewhat limited, but in general, the consensus is that it is a reasonable assumption for the controls in 2020. As you go forward in this discussion, you'll see that we strongly recommend that you start with 2020. It's an excellent foundation, and then customize it for Class 0, the charge board event, cable discharge event, and the charge device model. Here is objective evidence of the need for that customization. What we're looking at is yield information from manufacturing, and each data point is confirmed ESD damage within the manufacturing process. And each colored line represents a different product. So you can see that some products like this one were very sensitive with high losses as high as 22%. Others were robust and had very small, very low levels of ESD failure rates. Now, in this time frame, there was an S2020 program in place. It was a good program, not perfect, but it was a good 2020 program. And they scored 39% on our best practices benchmarking. So we were not surprised to see the substantial improvement after this company implemented the charge device model, countermeasures, cable discharge, and charge board event. So those controls were phased in quite swiftly at this point in time, and over just a couple of weeks, you can see that their yields improved dramatically, stabilized at a much lower level, and as they improved on their program, their benchmarking score improved, and they now enjoy almost 97% yields. And the devices today are class 000 sensitive with the same high level of yield. So these countermeasures added to 2020 give you a very robust program capable of handling extreme class 000 device sensitivities. ESD has always been thought of as both a quality and a reliability issue. If you're fortunate, the failures happen immediately. They happen in-house, you replace them, and move on. I will show you an example later on of an instance where we had catastrophic failures. In fact, there were close to 100% failure rate of devices in the class 0, actually class 000 region. The damage can also be cumulative. Subthreshold events, multiple subthreshold events can weaken the device and render it less robust. We have a question about can we give examples of CDM, CBE, and CVE controls? Yes, we'll get to that later on in the presentation. So, again, the damage can be cumulative. And worst of all are latent failures. Failures in time due to prior damage, which we've also experienced. We saw it by accident, but it was real and irrefutable. So we know that it does happen. We just probably will never be able to determine exactly how often it happens. Okay, here's a brief review of the charge device model and the charge board event. This slide, number 11, in a moment I'll show you the animated representation of the charge device model. And here you see a device sliding out of a shipping tube, landing on a conductive surface. This simulates the charge device model, or putting it another way, this charge device model simulates a device becoming charged and then discharging through a low resistance ground. Now, what's very important to consider is this representation of the modeling. Here we have the capacitance of the device, and it is a direct indicator of the amount of charge Q that could be stored on the device. And as you can imagine, the higher level of charge that's stored, the higher the discharge currents will be. Also important to note is the contact resistance that's represented here. This becomes an opportunity for prevention of CDM damage. Now, what many people are unaware of is that the vast majority of failures today are CDM in nature. You might want to, in your own mind, guess how many overall, industry-wide, are HBM versus CDM. What percentages? Well, here is the latest thinking and wisdom on this. Andrew Olney, and the quality director of ADI, the Industry Council, Texas Instruments, Intel, and many other sources all indicate that 99.9% of the ESD failures today are CDM in nature and can also be occurring via the charge board event or the cable discharge event. Now, the important message here is that because the vast majority of failures are CDM in nature, that is where the highest element of risk is for class 0 as well. Here is a chart that illustrates the two models, HBM and CDM. I'll put them both on the screen. And here we have two images of components that have failed. Here at 200x, the HBM damage is that black spot there. Relatively large area of damage. And on the right, you see the transient that represents the HBM stress test. And you see the pulse duration is in the neighborhood of 160 nanoseconds with a 1 amp peak current level. CDM and the damage resulting from it is substantially different. You can see here at 4000x a microscopic pinhole. This is characteristic of the CDM event. And if you look at the stressing current, it makes sense because we're looking at a 1 nanosecond transient with rise times in picoseconds. In fact, the rise time is so fast that even with today's high-speed scopes, we have been unable to fully capture the rise time. Note, we also have peak currents of 13 amps. These both were at the same stressing voltage, by the way. So what we're saying is that CDM is substantially different than HBM. Therefore, the designed-in protection is different, and the manufacturing countermeasures are different. And we'll touch on those in a moment. Here is a case study done by Analog Devices and Andrew Olney and his team there at Analog ADI. The reason they undertook this study was an unacceptably high failure rate or return rate from customers. When they did their diagnostics in the FA lab, the signatures that they saw indicated electrical overstress. The damage was very extensive and inconsistent with ESD, or so we thought at the time. So what they did is to take this circuit board with the device in question, recognize it. Well, let me back up a moment here. The signature looked like electrical overstress, but when they took a closer look at the circuit and where the damage was occurring, it was not reasonable for it to be electrical overstress. It was inconsistent with an external power supply issue, which drove them to evaluate the charge board event. So what they did is what you're looking at here, this field plate, is part of a commercially available charge device model simulator. And they've adapted it for circuit board testing. So what they've done is to charge this circuit board to desired levels, voltage, and then from above, a low inductance ground probe comes down to discharge the board and device at designated locations. The next slide, you're going to see the resulting damage, and this is where the surprise occurred. Here on the right is the damage that resulted from that stress in the previous setup. And as you can see here at 200x, the failure level is massive by comparison to the device alone. Here on the left is the same image I showed you earlier at 4000x, CDM damage and a microscopic pinhole, whereas here at 200x, previously to this work, would never have been considered an ESD issue. So Analog Devices went back through their records and reassessed their determinations of failures and determined that somewhere in the vicinity of 50% of what they previously categorized as electrical overstress failures were actually ESD due to the charge board event. This is an incredible discovery. It takes ESD out of the realm of a significant problem into what many argue to be the #1 assignable cause of electronic device failure. Others have done work, like Nokia, and their results come back with a very surprising result. The peak discharge current for the charge board event can be as high as 25 amps. which is incredible. Now, if you'd like to know more about this, this case study is described on our website, and we have videos here down in the corner. You see there's a video of Terry Welcher performing the charge board event. I think you'll find that very interesting. Okay, benchmarking. This is a chart that represents the benchmarking that we do, and as I mentioned earlier, is 90% accurate over the phone, by the way. We can interview you and tell you with 90% accuracy how you're performing to best practices. Each bar in this chart represents a company. Number 3 was company X as an example. And you can see the red lines, the red bars are defense manufacturing companies. The green lines are contract manufacturing, and we have some aerospace data points here at number 12 and 9. We frequently find companies on first visits in this region. We also would indicate that this region poses high risk for a class, especially class 0, but in general, the practices are not up to best practices. They could be, and often are, in compliance with S2020, but as we said earlier, there's a need to go well beyond that. We have, as you can imagine, visited countless sites since forming Dangelmeyer Associates in 2001. And since leaving AT&T and doing these assessments, we have yet to go to a site that has adequate CDM and CBE controls on the first visit. In fact, none of the companies we've been to are fully aware of the pitfalls of using a field meter. It's an instrument, ESD 101 instrument, and yet it's very seldom that we find people that fully understand the pitfalls, and it's rare that they use it correctly, is the bottom line here. Okay, so who's at risk? Well, here is a list that we're going to summarize each of these in a few minutes. One of the first ones is companies without data, without CDM thresholds. Semiconductor back-end is an obvious scenario where the devices are first assembled and at risk. Automation can create what we kiddingly refer to as mass murder. If things are out of alignment, you can systematically damage or wound devices. HBM programs in general are at risk of CDM class 0 failure rates. And as you know, 2020 is good, or advertised to be good down to 100 volts. Circuit board manufacturing in general, because of the charge board event, as well as system integration. Contract manufacturing, defense, aerospace, consumer electronics, medical, automotive, wafer fabrication, and wafer saw. I think you'll be interested in this case study here on wafer saw. Very interesting. And of course, new construction. There are considerations that are generally completely overlooked. Okay, companies without CDM thresholds. This is one of the greatest risks. As I mentioned earlier, we had catastrophic failures, 100% failure rates, and it was due largely to the absence of data, and I'll show you that example momentarily. The question is, if you don't have the data, how can you prepare for class 0? If you have the data, you can handle almost anything. It's not easy. It requires considerable attention to detail and a lot of issues, but without the data, you're going to be blindsided and run into major issues. Again, we have clients with devices down in the 1 to 3 volt sensitivity and nearly 100% yields. So based on our experience, most companies are at risk for this issue. Some have HBM thresholds. Unfortunately, many do not, but some do, which is a good start. However, very few have CDM data. And as we said earlier, 99.9% of the ESD failures today are CDM in nature. Therefore, CDM is the greater risk for class 0. Certainly HBM is an issue as well, but CDM is the greater risk. The other scenario, even though HBM and CDM do not correlate, there's no way to predict one from the other. On average, CDM thresholds tend to be lower than HBM. So the question is, are you on a collision course, like the perfect storm? I don't know how many of you remember the perfect storm from 1991, but here on the East Coast, we're keenly aware of it. It was a severe weather event, and it actually had a wind field larger than Katrina. The hurricane force conditions extended 2,000 miles up and down the eastern seaboard, with devastating destruction on land and sea. Now, the analogy that I'm coming to here is that CDM is generally not understood, nor are the countermeasures, and the data is generally not available. When you add to that the trend toward class 0, the risk is substantial. What we're talking about here is a very real threat, like the perfect storm. People don't understand CDM typically. They don't have the data, and the trend is exposing you to more and more frequent use of the class 0 devices. So therefore, the risk is it's like a storm coming in the night, and often people experience it with catastrophic 100% failure rates. Here is the example that I mentioned earlier. Now, I'm not going to go into all the details in the interest of time, but I do want to point out that this was a case where Bell Laboratories knew they were putting into production an extremely sensitive device, but there was no process in place to communicate that information, and it just wasn't deemed a high risk. So you can see the results here. We had 100% failure rates in many instances, with wild variation in yields across the time. This was during ramp-up of a $1 billion product line, and it was brought to a complete standstill. We were literally meeting with the vice presidents of AT&T on a weekly basis. I can assure you this is not a place you want to be. So word to the wise, get the data, and I'll emphasize that more in the upcoming slides. Okay, what about the availability of device data? Well, unfortunately, this is the situation. If you go to the data sheets, you'll find that roughly 75% have HBM data, and only 10% have CDM data. This makes it difficult because it's like pulling teeth sometimes to get the information. Now, on the other hand, JEDEC has device qualification requirements that most companies are adhering to, most IC suppliers. And in these documents, HBM and CDM is required. So what that means is that if you are trying to get data and having trouble getting it, Let me see. Somebody has a hand raised. Okay. Jim. Let me try this now. Jim, see if you can talk to me. See if we can hear you. For some reason, I can't hear you. Is your mute on, Jim? Okay, that feature doesn't appear to be working. So let's, if you could send me a text with your question, we'll handle it that way. Okay. Oh, yes, okay. I am going to talk about collecting data as well. Good question. So yes, this is the information that what we know exists. So one key here would be to call your IC suppliers and ask for the qualification report instead of data sheets. Can't find it in the data sheets, contact them for the qualification reports, and sometimes you'll get it that way. It is frustrating, to say the least, because the IC suppliers make it difficult to get it. They argue that no one is asking for the data. Personally, I think that's because it's happening at levels where it's just not visible. We know people are asking for it. So one of the suggestions you could take would be to send a letter at an executive level requesting the data. You know, the squeaky wheel principle may help us here. So ask for CDM and HBM thresholds or who to connect for the data in the future. Now, if that does not work, contact me. We often have colleagues that we know in these companies in influential positions. And we're working that issue now and have had some success getting data that was otherwise very painful to get. So anyway, if you've sensed some frustration on my part, it's real. I share your frustration too. It's much more difficult than it should be. Okay, circuit board manufacturing and system integration. Key areas to consider. Why? Because the circuit boards are exposed. If the circuit boards are exposed, that means that random access to the various conductive elements of the board are available for contact. If you are fortunate enough to have a stress come in through an edge connector, the input protection of the board may suffice. But during manufacturing or system integration, the boards are exposed to random contact. So we're going to start by talking briefly about a very widespread myth. It's almost universal or assumed that circuit boards are less vulnerable than devices. And in reality, it's just the opposite. As we mentioned earlier, discharge currents as high as 25 amps are not unusual. So in fact, boards are more sensitive than devices by themselves, again, when they are separate from the enclosures and available for direct contact. Nokia asserts that all of their ESD failures are happening at the board level, that they rarely find them at just the device level. I don't know that I can buy that, but it's a good illustration of just how important this failure mechanism is. The probability of a class 0 device in your designs is rapidly escalating. And keep in mind, as we said earlier, many companies do not have CDM data. And there's a tendency to think that if you don't have the data, you don't have a problem. And we learned from ADI that 80% of board failures are often ESD at the board level, or CBE. We actually had one client where we implemented charge board event countermeasures and reduced their electrical overstress failure rate by 80%. So 50% is a good rule of thumb. Okay. Why is this? Why is the charge board event so much more severe? Well, here's an illustration of it. And also, to one of the questions earlier, I think it was your question, Kevin, how do you get the data for device sensitivities? This chart will help you estimate the device sensitivities. We don't advocate estimating it, but in the absence of any data, this will give you some indication. In this chart, as we go from left to right, the package size for the component is increasing in size. You can see over here that the pin count goes from 1 up to 1,000, or the package area size. Basically, the larger the device goes from going from left to right, the package size is increasing. Going from top to bottom, we're talking about higher operating speeds. So what that means is if you have a large device, the CDM withstand voltage is likely to be worse. It's likely to be much more sensitive. And as you go into higher operating speeds and the feature sizes that come with it, you're also likely to see greater sensitivities or lower thresholds. So that means here we have the class 0 region over in the lower right-hand corner. Large components physically at higher operating speeds. So again, this was work done by the Industry Council, and it's a reasonable way to make an engineering approximation, but there's no substitute for getting the actual withstand data from your IC suppliers. And I would encourage you to go after it and let them know that we need it, because they're coming back saying nobody's asking for it. Okay. Here is the waveform from the stress test that I showed you earlier, the analog devices case study. Here is the current failure level, device failure current level is right here at about 5 amps. When the device was stressed by itself at 250 volts, the peak current was below that failure point. Whereas at 250 volts on the circuit board, peak currents exceeded the device failure point and approached 9 amps. So clearly the risk at the board level is more significant. And notice that we're talking only 250 volts. This is the class 0 point for devices. But for a circuit board, even a circuit board at 100 volts is at risk. It's a high risk at 100 volts. So later on when we talk about circuit board classifications, keep this in mind. Now let's see, we have another question here. Okay, I don't see a question. Not sure why that came up. Oh, I see. There it is. Is the slide package available for us to print? You'll be able to view this on our website. The whole webinar is being recorded, so you'll be able to go back and get it that way. If you need a PDF in addition to that, send me a request and we'll take care of it. Thanks for the question. Okay, here is another slide that shows the variation that we see in discharge currents of the charge board event. This is work done by Nokia, and you can see depending on the countless variables on a circuit board, you can get dramatically different results. And here are some of the peak currents. Oh, here's one over 20 amps, 15 amps, that's probably 17, 18 amps. Considerable variation, which is also one of the reasons that we doubt there'll ever be a charge board model. That's why it's referred to as an event, charge board event, rather than model. There are just too many variables to actually model or create a universal model. Okay. Here is an example, real-world example of a charge board event. And it was an interesting case study that we worked on for many months to get to the bottom of it. And what we're looking at is a legacy product that had been in production for years successfully. And then overnight, we started experiencing 40% failure rates. When we looked at the device that was failing, its CDM threshold was very good. It was at 1.5 kV, which is actually the highest meaningful number that you can get from that test due to corona discharge. The potential on the device will bleed off. It's very difficult to keep it at potentials higher than 1.5 kV. Anyway, after months of investigation, we found it was related to changing suppliers for the faceplate. Here we have a plastic faceplate that with the original manufacturer was prone to charging to about 1,000 volts. With the new circuit or faceplate manufacturer, it was more prone to charging to 10,000 volts, even though it was done to the same specification. So digging more deeply, we found that the new supplier was using a different mold release, which changed the morphology of the surface, making it prone to charging to higher levels. So here you have a 10 kV source at the edge of the circuit board over here. Then in production, during in-circuit test, a bed of nails pins come up from below to do the test. And one of the contact points was right here at this transformer. That created the discharge. This pin was connected to pin 36 on the device, and pins 21 and 22 failed as a result of this discharge contact point at the inductor, transformer. By the way, it's not unusual for CDM to occur that way, where you stress one pin and others fail. Okay. Now, how do we classify circuit boards? How do we use this information? Well, one is, and this one has been around for some time, and it has merit, and that is to base the sensitivity of the board on the most sensitive component. What does that mean? That means you need the data. You must have those thresholds. And I can't emphasize that enough. Very, very important. Estimates really are not sufficient. So without the data, you're at risk. Another consideration is to classify circuit boards as class 0 because of the charge board event. Other considerations include these that you see here. One would be the criticality of the application. Also, the board size. If it's a small circuit board, it is less of a risk. The discharge currents won't be as high. A large board, on the other hand, is problematic. Also, using the CDM data and knowing that you could see 25 amp discharges. I'm looking at one of the questions here from Don. Thanks, Don. Okay, Don's asking about using TBS diodes to raise the ESD level. Absolutely, those are considerations. What I can tell you, Don, is that we have recently expanded the scope of what we do. In fact, we were just on a call with Jeff Donahue, and we have a means of actually scanning and observing the current flow in circuit protection circuits, I should say, that would indicate whether a TVS would help or not. And sometimes shielding or other strategies work, but there's now a scientific way of determining that. So we probably should talk about that later. It's a very interesting but complex topic. Okay, contract manufacturing. How many of you use contract manufacturing? I expect quite a few. In general, contract CM programs are based on 2020, which is an HBM-centric document. Now, I want to hasten to add that the next issue of 2020 is coming out shortly, and it will indicate CDM at 200 volts, which is an estimate. There is very little data to substantiate that. Based on our experience, the programs that we see in factories are not robust enough to make that assertion. So I take that carefully, or consider that wisely, because we're skeptical that it really is accurate. Okay, so what does that mean? In general, I see outsourcing as another potential perfect storm. Generally, the customers, the OEMs, do not specify Class 0 requirements. They leave CDM and Class 0 controls to the CMs. And CDMs they wait for the requirements to come from customers to take action. So it's sort of like finger pointing. It's their issue, the other person's issue, which leaves this wide open and certainly a high risk. Okay, defense and aerospace manufacturing. Well, they are consistently working to HBM standards. Some of them are still using the military standards, which are 30 years outdated. And it's rare that when we first go to these companies that they are focused on CDM or CBM. Even by the subject matter experts and executives, they often do not understand the risk or the nature of the countermeasures. There is a disappointing complacency with using HBM techniques. As I said, military standards are 30 years outdated. 2020 is much better. It's probably only 10 years outdated, but it's definitely a good place to go. And by the way, I want to emphasize that the procedures in 2020, the HBM procedures, are absolutely essential, critically important for CDM and charge board event. If you have not done the countermeasures in 2020, you don't have a chance of doing CDM or charge board event countermeasures. So by all means, continue with 2020. You just need to expand the scope of what you're doing. And often in these areas, there is a reluctance or resistance to change. And there's some good reasons for it. If you were to impose CDM requirements today, abruptly, it would bring to a standstill many of the existing programs, which you can't do. So our recommendation is to phase in these controls. And a simple first step, if any of you have influence in defense or aerospace, or in fact any of your industries, start by making it absolutely mandatory to get CDM data. If you have the data, then intelligent people can take action and prevent things from happening without a mandate. So to me, this is a good first half step. Require the data, make it mandatory, whether it's through NASA or aerospace or one of the other organizations. This would be a great benefit to the industry. Okay, consumer electronics. They tend to be cost-driven, performance-driven, all the things that you and I want. Cell phones with smartphones, with high speed, etc. All of these things tend to aggravate the ESD sensitivity. And the combination is prone to class 0 thresholds and, of course, circuit charge board event issues. We also find that, not in all, but in many applications, the design qualification is incomplete. They may not have done the full set of, for instance, system-level stress testing, or set them at the right levels. Medical manufacturing, again, it's a 2020-based industry. The FDA has wisely recognized S2020. Oh, by the way, none of the industry standards give you, I'm going to mention this in a minute coming up, but none of the industry standards provide all of the CDM countermeasures that you need. So the FDA is doing the best they can in that sense. In this case, the failures are life-threatening, so it's an important issue to consider. And we have found that fairly often, with the design qualification being incomplete, they don't have device thresholds, and the system-level stress testing is inadequate. And the result of that is that we have seen quite a few instances of reliability failures because of these issues in the medical field. Automotive manufacturing, a similar scenario. Here, the transition is going from primarily mechanical to electronic, and that can pose its own problems. It's a whole new learning curve. And if you think about it, there are charge cables in the construction of a car or assembly of a car have got to be a significant issue, as well as the charge board event. Now, in the repair area, I can almost guarantee. In fact, my son was studying automotive, technician. He went on to computers since then, but he can confirm that there are virtually no controls in the automotive repair business. New construction. This is an area that is almost always overlooked. Frequently, the ESD engineers are not involved in the early phases, which means that the architects or facility engineers are making ESD decisions without the subject matter experts. And the penalty can be catastrophic. We've seen cases where floors had to be replaced and major changes to automation or assembly lines. You may even need to segregate Class 0 lines from other areas, which means relocating things. And it's just an area, word to the wise, if you're outfitting new lines or getting into new construction. This is the ideal time to consider ESD. For instance, flooring. There are many good choices out there. Some of them are high charging, and others are low charging. If you're putting in a floor, and you have to put in a brand new floor in a new building, why not get both a conductive floor that's not only conductive, but low charging? For instance, conductive vinyl is a very commonly used floor, and it's high charging. I found this out the hard way. We redid a major area at AT&T with conductive vinyl and had people complaining frequently. We had people complaining frequently about getting zapped in the area because of the vinyl. They were walking in the area in non-ESD shoes. We didn't require everyone to be grounded. Only those that worked in standing operations needed ESD footwear. And those that had regular street shoes were getting zapped left and right. Arnie's just made a good point that as you get into construction, you know, you're going to be getting into new construction, and it's almost invariably not considered and ends up requiring change later. That can be very, very costly. Okay, here's another interesting area. For decades, wafers have been assumed to be virtually immune to ESD failures. That's changing. We have clients frequently reporting ESD failures now at the wafer level. And as I promised earlier, we're going to talk about a case study in wafer saw that was very surprising. Terry Welcher and Lou DeSharo on our team did a very advanced, sophisticated mathematical modeling of wafer and ESD stresses to wafers. I won't go into all the details of this, but simply put, this modeling represented typical wafers, and it took into consideration different feature sizes, large and small, and neglecting certain issues, surface resistance. And the assumption was that the stress would come to the back side of the wafer, which is what we see all the time in wafer fabs. You know, you have great care to avoid physical damage to the active side. So therefore, you know, the discharges typically occur to the edges and backside. For this evaluation, the assumption was that the stress would come from the backside. And by the way, it's very common in wafer fabrication to have 5,000 volt strikes or discharges to the backside of the wafer. The results of this work showed that on the active side, now this is, again, the stress is on the backside at 5 kV, the rear of the wafer. We were measuring up to 200, or calculating up to 250 volt stresses on the active side of the wafer. And depending on the specific parameters of a wafer, this, of course, could change. The bottom line is that you're going to start seeing, if you haven't already, ESD failures at the wafer level. Wafer saw. This is a back-end operation, and it's underwater, literally, and historically been assumed to be a ESD risk-free operation. Well, Class 0000 hit this particular wafer saw operation and resulted in 92% failure rates at the wafer saw operation. Very surprising. And the failure analysis confirmed that it was ESD damage. Now there are several, let me go back here just a sec. There are several techniques that are involved here, but event detection is one of the better choices. You can monitor ESD events in the wafer saw operation to determine if they're occurring. In this example, the problem was resolved by adding CO2 bubblers to the water, which helped, did not solve it. It also required a change in blade, saw material to reduce the frictional charging, as well as the speed of rotation and depth of cut. So there were several variables that had to be adjusted to prevent this problem from occurring. Okay, now we're going to get into just a few slides left here for countermeasures. Well, how do we deal with these problems that have been identified. First is to remember what we said earlier, that the industry standards, none of them, include all of the CDM countermeasures that you need. For instance, the surface resistance is an excellent way of controlling and preventing damage. It's also unlikely that standards will include Class 0 countermeasures in the future. The reason for that is that there is invariably a high level of customization for extreme sensitivities. Therefore, it just does not lend itself to standardization. And as we've said, the understanding CDM and its mitigation is not well understood, and will not be included in the 2014 issue of 2020. In other words, the 2020 will have some improvements, but they really don't do much for CDM. Even though the scope is going to now mention CDM, very little has changed in that regard. And as we said earlier, the 99% of the risk for device failure today is CDM, charge board, and cable discharge. Now, the good news is that once you understand CDM, the countermeasures for the charge board event are, in concept, the same. The physical changes are different, but the concepts are the same. So the assumption here, or the conclusion that we're drawing, is that Class 0 controls are largely CDM controls and must be fully understood in order to prevent these issues. Now, there are proven CDM practices. Unfortunately, they're not in the public sector at this point. We do have them and can discuss them. And I can tell you that I think it's common sense, that the countermeasures will have to escalate as you go deeper into the Class 0 region. And certainly when you get below 50 volts, it gets pretty dicey. And in fact, this is another reason to get the device data up front. If you can get it early enough, you can avoid these Class 000 devices, or if it's at all possible, avoid them. Try to keep them out of your product designs. Okay, a little more description about the countermeasures. Here we have the representation of the CDM modeling, or CDM model. The objective is to reduce discharge currents. It's the current that causes failure, not voltage. So there are a couple of ways of doing that. One is to keep the voltage low on the device. If the voltage is 0, you're not going to have an event, and you're not going to have discharge currents. Unfortunately, if you're dealing with let's say a Class 000 device that has a 1 volt ESD threshold, what are the probabilities that you're going to be able to keep that device voltage consistently below 1 volt, or 10 volts, or even 100 volts? It's not likely. So that has its drawbacks. Now, the other opportunity is to manage the surface resistance at the interface, or at the point of contact between your product and ground or any conductive object. This is a viable remedy as well. Now, there's a question here. Which one of these is already covered in S2020? And we get a mixture of responses for this, but the answer is it's the voltage. It's the 100 volts, keeping people below 100 volts. And it is definitely a critically important procedure. However, as I said it becomes increasingly difficult as you get into extreme sensitivities. Surface resistance, on the other hand, is robust and durable and less prone to human error. How do you keep voltages down on the product? Well, you have ESD mats, wrist straps, and ionizers. Valuable tool. However, they're prone to human error. They're often facing the wrong way, turned off, dirty, not calibrated, etc. Whereas if you take a material with the right properties and put it in just the right location, you can prevent damage, and it will need minimal maintenance. For instance, tweezers. How many of you are using metal-tipped tweezers? That is a very high risk for a charge board event, for components. If you substitute a pair of static dissipative tipped tweezers, that risk is greatly diminished, if not eliminated. Unfortunately, you can't just pick something off the shelf. There are many tweezers out there that claim they're ESD safe when they're not. For more information on this, we have, again, educational videos on our website that show you this phenomenon. You'll see tweezers that work and don't work, and you'll see the charge board event, etc. So go there and check it out. There's also one there on event detection. That's a powerful tool for analyzing these situations. Time prohibits us getting into all of that on this webinar. We'll get into the, in fact, if you have questions or any suggestions for future webinars, let us know. We'll be glad to entertain them. Here is an example of the material problem that exists. Let me back up again. Here is the surface resistance question that we just talked about. If you use the right materials at the right place, you can prevent charge board or charge device damage. Here's an example of JEDEC trays that we see consistently throughout the industry. This one is particularly of interest. Here on the same tray, we find two conditions. One is that the area we tested was too high in resistance, and it was charging to 142 volts. Another part of the same tray, we were measuring 4 times 10 to the third ohms surface resistance, which is too conductive for the charge device model or the charge board event. These trays are being used by the millions throughout the industry. And I think it's another perfect storm waiting to occur. Oh, we have a question. Arnie has another question. The trays don't look the same. Well, yeah, maybe they're not. I know, well, let's see. They do look a little different. Thanks, Arnie. I can assure you that it looks like this one is not the same as this tray, but we have, it was a case where we had, this data was taken on the same tray. What I'm saying is we've seen it in many cases where on the same tray we get these extreme conditions. These look like photographs from different scenarios, but the message is the same. It is something that does occur. And then back to this slide. What we're saying is, as good as S2020 is, and even the 2014 version, as good as it will be, it does not include enough for charge device or charge board, and those countermeasures need to be added. Okay. Any further questions? Good questions along the way. If you have any questions going forward, please feel free to send them our way. We'll be glad to respond to you. and we'll look forward to seeing you on our next webinar. And thanks very much.